we're very happy to have Federico Galetto. Did I say that right?
Perfect.
That's great. From Cleveland State, who's going to be telling us about some computational methods.
All right. Well, thank you, Trisha, and hi, everyone. I go by Fred, he, him. I'm going to tell you about computational methods, and I'm going to jump right in. I will say one thing first for practical reasons. I decided to kind of switch back and forth between the slides and the board. I was told for Zoom people, I can only use this part of the board. So we'll try to concentrate it in here. Also, everything that I put either on the slides or on the board is already in the notes that are available online. So you don't have to worry about missing anything if you can write everything down. Okay, so I want to start with some motivational problems. So we are taking some polynomial ring with coefficients in a field, and we take an ideal I, and there are some things that we might want to know. For example, if we take a polynomial f, does that polynomial belong in the ideal or not? You might also say, well, if it belongs in the ideal, how can I write it in terms of some generating set? Oh, okay. My generators didn't make it on the slide, but I take f1 through fr to be generators of my ideal. How can I write my polynomial f in terms of those generators? And also, if I have another ideal, how can I check if I and j are the same, right? Maybe to give you some motivation, some of these problems actually come from geometry. Oh, what was the deal here? Middle? Middle? Yes? Okay, so, right. So we heard yesterday from Claudia that you may have a variety, and you have, that is the set of points in space over which all the polynomials in your ideal vanish. And then in the example you had yesterday, you had some boring equations, right? The one that are 0 on all those points. So f belonging in that ideal means exactly that. So if you have your variety, a polynomial f in the ideal, pretty much by definition is 0 on this variety. So you might want to know it belongs in the ideal for this kind of reason, okay? But then maybe this one's a little more interesting. Two ideals are the same, but they might be given by different generating set, right? So it might not be obvious that they're the same. But of course, if they are the same, they define the same geometric object. And so you might want to know that, right? So this is useful. So I'll refer to the first problem as ideal membership, and this last one here is ideal equality. And maybe I should say here, the converse is not true always. You might know about that, but that's kind of beyond this. Also, can everyone hear me okay? And can everyone see okay? All right, great. So I have another set of motivating problems, and I call this quotient representations. If you have your polynomial f in your ring, you might want to work in the quotient or mod I, because again, we already heard these quotients are coordinate rings, these are varieties. So we want to study those. Well, how should we represent the coset of f inside this quotient, right? I'm thinking, if you think about basic examples like the integers, if you take the integers modulo some positive integer m, then you have a pretty well-defined choice of representatives. And we wish we could do the same for polynomial rings when we quotient by an ideal. So that's what I'm aiming for here. And then also, again, more motivations from geometry. Can we determine if two cosets are the same, even if they're given different representatives? Well, what would this mean if f and g represent the same coset? It means that the difference belongs in I. And so this difference is one of the boring functions that vanishes on your variety, right? But what that tells you is that the polynomials f and g actually represent the same function as a function from your variety to your field k. So different polynomials may represent the same polynomial function, and they do that exactly when they have the same coset. And then one step beyond that, R mod I is actually a k-vector space. Can we find an I basis for it? And that we will use later on for some useful computations. All right. So these are some of, the only motivating problems for computational algebra, but some of them. Before we go to more general settings, let me say that there's a case that we understand pretty well, and that is the case of polynomial rings in one variable. Those rings are Euclidean domains. We have a Euclidean division. If I take two polynomials f and g, g is non-zero, I can divide f by g. We know the procedure of long division. We get to write f as a quotient, q times g plus a remainder. The remainder is nice in the sense that it's either 0 or it has smaller degree than g. If you set things up right, then q and r are both uniquely determined, which is pretty nice. Okay? So because of this basic result, we can actually answer all the questions in the univariate case. Of course, imagine writing f like that. Well, f will belong in the ideal generated by g if and only if the remainder is 0. And then, of course, f and the remainder will represent the same coset, because when I mod out by g, g goes away. And so in particular, I might choose the remainder as my preferred representative. And then finally, when I mod out by g, essentially, I can represent everything as a linear combination of the powers of the variable up until I hit x to the whatever degree g has, because then everything else gets rewritten when I take the quotient. All right. Any questions so far? All right, then. So let me start introducing the more general setting. So when you think about this setting here with long division, what's the first thing that you do when you want to divide f by g? If you write out long division by hand, right? How would you write f and g? Sure.
Try to divide one leading term by another leading term.
Absolutely. So you already know what leading term means. In a sense, it should come first, right? Coming first means that there's an order of the terms that make up your polynomial. So typically in one variable, you're just told order them from the largest to the smallest power, which is pretty natural. So we have to talk about what happens when we have more than one variable. So let me set some notation or definitions first. I call a monomial a product of powers of the variable. So for short, I'm going to write x to the a, it's x1 to the a1, x2 to the a2. I might need to refer to the a as the exponent vector. All the entries are non-negative integers. And then if I want to know the total degree, I might just put bars around a, and I call that the degree of x of the monomial x to the a. I should also say that, and this will come up in other places later too, that different sources give these things different names. So some of my references would call this a term, where I call this a monomial. And sometimes I also get confused. So, all right. Apologies in advance. Okay. So how do we order these monomials when we have more than one variable? Well, so there is kind of a nice way to do it, but it has some requirements. So we're going to introduce this idea of a monomial ordering. So it's going to be an order relation on the set of all monomials in your room, right? So you have this big infinite set with all the monomials. You want to put an order on it. So that's a relation that is reflexive, antisymmetric, and transitive. But it needs to satisfy other conditions in order to be useful. So first of all, it has to be a total order. So given any two monomials, as long as they're different, I need to be able to say which one is smaller and which one is bigger. Okay? So total. Second property we require is that this order be compatible with multiplication. So if I have two monomials, m1 and m2, and I already know which one is smaller, if I multiply this inequality by a third monomial, the product should respect that inequality, right? So if I multiply by m3, I should see the inequality go in the same direction. And there's a third condition, and that says that I want 1 to be the smallest monomial of all. In one of the problems, I'll ask you to maybe, actually, there's a bunch of problems that deal with monomial orders, but you can rephrase some of these conditions in other ways that are useful for some proofs. But this is the definition that I'm going to adopt. Okay. Again, I'm sorry, maybe if you're trying to write everything down, this might be a little bit fast, but as I said, everything is on the notes, so don't worry about that. Let's do some examples of these. And I chose some of the more basic ones, the ones you typically encounter. So you might want to take a moment to actually prove these things are monomial orderings in the sense of the previous definitions, but I'm just going to go through them and see how you can use them in practice. So one that is pretty natural is the lexicographic order, which essentially mimics the order of dictionary words. So you would agree that you have your variables, let's say x, y, z, x comes first. So anything that has an x should come before anything that doesn't have an x. And if two things both have x, then the one that has more x's, so a higher power of x, should come before that. Okay. So the way you can do this more formally, if you want, is you write out the exponent vectors of your monomials, call them a and b. You look at the difference, and you ask that the first non-zero entry of a minus b is positive, which tells you x to the a should come first. I'm going to show you some of these in an example. So although it's pretty natural and also important for some theoretical points of view, the lexicographic order is not typically one used in practice unless you want to hit certain specific applications. So there might be better choices. The graded lexicographic order is sort of the next natural step. Here, one funny thing that happens with the lexicographic order. Suppose you even have only two variables, right? X is bigger, so let's do this in two variables. X is bigger than y to the 100, which it may seem like a strange thing to do, right? But if I follow the approach that I gave in that definition, this monomial has exponent vector 1, 0. This monomial has exponent vector 0, 100. And if I take the difference, the first non-zero entry is positive, so this one should come first. So if you don't like that, you might say, well, hold on, I'd rather bring in the total degree first. So you introduce this graded lexicographic order that says x to the a goes before x to the b if it has larger total degree, or in the case the total degrees are the same, then I fall back to the lexicographic ordering. Okay? And the final one that I'm going to present here, graded reverse lexicographic order, is still graded, so it first checks for total degree. But then, if the two monomials have the same total degree, you have to look for the rightmost non-zero entry of the difference of the exponent vectors and ask that it be negative. So I'm going to show you an example slightly bigger to hopefully make sense of this. So the example that I chose has these monomials: x to the 4 plus x cubed y squared z to the 4 plus x y to the 5 z cubed, z cubed, sorry. Well, I chose an order already to write this down. The order I chose is the lexicographic order with x going first. So x to the 4th is bigger than x cubed, and that's bigger than x, so that's pretty straightforward. So this is for lex. Okay, but what if I want to rewrite this in one of the other orders? Okay, so we agreed that with the graded orders, we look at total degree first. The total degree of this one is 4. 3 plus 2 is 5 plus 4 is 9. And this is 1 plus 5 is 6 plus 3 is 9. So these two have the same degree, and they're both bigger than that. All right. So which one should go first? Again, I can do it with the exponent vectors. 3, 2, 4, minus 1, 5, 3. And I get 2, minus 3, 1. The leftmost non-zero entry is positive. So this one should go before that one. So in Glex, this would be x cubed y squared z to the 4, then x y to the 5 z cubed plus x to the 4. All right. Now, when you do this, you also notice that the rightmost non-zero entry of this difference is positive, which tells you that if you switch the order of these two vectors and then take the difference, the last entry is going to be negative. And what that is telling you is that if I want to look at the graded reverse lexicographic order, then this one should go first. So I'll write it down here in grevlex, x y to the 5 z cubed plus x cubed y squared z to the 4 plus x to the 4. Okay? So I should say this, if you do computations with software, like Macaulay 2, for example, then this is often a good choice. In fact, it is the default choice in Macaulay 2. If you don't specify an order, this one will be used. You might choose another one for particular applications. And there are also more orders. In particular, there's one that I'm going to ask you to explore in the problems because we will use it for the second day lecture. Okay. How do we feel about this? Any question? All right. So let's introduce a few more definitions. So we heard about this already. Lead term or leading monomial or lead monomial, the leader should come first, right? So if you fix an order on the monomials of your polynomial ring and you take a polynomial, you can write it out as a linear combination of monomials, always. And then the largest monomial in the order, whichever you picked, is called the leading monomial. I will denote it with Lm of f. It may come with a coefficient that's not equal to 1. That's okay. We call that the leading coefficient, Lc of f. And then you might combine them to get what you actually see in the polynomial. So you multiply them and you get the leading term. And again, some of the sources switch term and monomial, and I might eventually forget which one I chose. So sorry about that. Questions? No. Okay. All right. So obviously, because I wrote them in order here, the leading monomial is always first and the coefficient is always 1. So maybe that's not the most interesting example, but all right. Now, I'm giving you the theorem first. I want to show you the statement, and then we will not prove it, but we will actually see how this works in practice. So the point is that you can actually construct a division even in a ring that has more than one variable. And it goes like this. So you're going to consider a tuple of polynomials, and that's what we will be dividing by. So we may divide by more than just one polynomial. So I call that capital F. I take S non-zero polynomials. Well, they should be non-zero. And I fix a monomial order. And now if you give me any polynomial f, I can divide by the tuple, which means I can find some quotients q1 through qs, some other polynomials, and I can write f as a sum of these qi times fi, but there might still be a remainder. What do we ask of this remainder? It can always satisfy these properties. It's either 0, or if it's non-zero, then we can write it as a linear combination of monomials, in which case we can ask that it is a linear combination of monomials, none of which are divisible by the leading monomials of those polynomials over there. Okay? So this is a little bit formal, but I'm going to show you an example in a moment so that hopefully we feel better about this. Okay. In fact, let's do that. Now here, I think I already need more space. So I'm going to bring down the middle again. Okay. So the polynomials I chose for my example are like this. F is x squared, y squared minus y cubed. F1 is y squared minus x. And F2 is xy minus 1. And I want to use the graded lexicographic order. So I just want to make sure that they're already in the right order. This is degree 4, this is degree 3. So that's fine. Degree 2, degree 1, degree 2, degree 0. Okay, so that's easy enough. I want to divide my f by the tuple or the pair f1 and f2. And when I write this, I mean in this order. F1 first and then f2 second. Okay, so then after that, I'm going to do it basically like you would normally, like you would for long division. So I'm going to write my, let me put F1 here, F2 here. I'm going to divide my F, so I'm going to put it here. And now I'm going to start the process. I'm going to divide by this one first, then by that. So I look at the leading monomial, x squared, y squared. And I have to see if it is divisible by the leading monomial of this one, which it is, right? X squared, y squared divided by y squared gives me an x squared. So I'm going to put that up here. I need two lines here, one for the first quotient and one for the second quotient. So maybe I should do this. Okay, so now that I have my first quotient, I multiply this back by this line. I put it down here and I subtract. So it looks like on division. X squared, y squared minus x cubed. And then I subtract. And of course, this is designed so when I subtract, these two go away, right? So nothing here. But then what do I have? Minus y, well, I should put them in order, right? So x cubed minus y cubed. Yeah. And then I keep going. So now I have this one and I try to divide it. The leading term is x cubed. Is it divisible by the leading term y squared of this one? No, it's not. Is it divisible by the leading term here? It's not, right? So what do I do with this one? I set it aside. So let me circle it for now. I'm going to kind of forget it for the time being, but we'll use it at the end. So at this stage, I'm just going to take minus y cubed. Yes? Should GLAX, it should. I'm using GLAX.
Oh.
Yeah. No. That's okay. All right. Now I keep going. I have this one. This is just a monomial. Can I divide by the leading term of this one? Yes, I can. So I'm going to have another, what is it? Minus y here for my quotient. Then this minus y multiplies this one. So I get minus y cubed plus xy. And then I subtract. So I'm going to have to start using the other board. All right, let me try to continue along here. When I take the difference, the y cubed cancels out, but I have minus xy left. And this is my next step. So once again, is this divisible by y squared? No, it's not. So I go to the next. Is it divisible by the leading term xy? It is this time. I have a quotient. Oh, I need to switch again. I have a quotient here, minus 1, right? And so let's see, now minus 1 multiplies and I get minus xy plus 1. I take the difference, this one goes away and I have a minus 1 left. We're almost there. This is a monomial. Is it divisible by the leading terms over there? It's not. So then I set it aside. Once I set this one aside, I have nothing left. And now I'm done. Okay? Yes.
So you put the F1 and F2, but you chose to divide by F1 first.
Mm-hmm.
Do you know in general which one went first to get the best result?
I think that, how does it go? You might want to have the smaller leading term first. I forget. There might be a criterion depending on what you're trying to do. Okay. But we're actually going to do that. We're going to switch them. Let me record the result of this first. So the Q1 and Q2 up there are going to be my quotients, right? But there were a bunch of terms that I had to set aside. I couldn't do anything with them. So those are going to live in the remainder. But if you notice also, when we do it this way, the remainder we constructed will satisfy this condition, right? Because the monomials we set aside are exactly the ones that are not divisible by the leading terms. So let me record it here. Hopefully red is okay. R is x cubed minus 1. That's a remainder. Okay, so that's the procedure. Any question? Now, you might say, if you want to try to mimic what happens in one variable, you might say, well, my remainder is non-zero, so my polynomial f does not belong in the ideal generated by f1 and f2. Okay? All right. Now, let's switch up things. I'm going to do the same thing, but I'm going to change the order. So I'm going to have xy minus 1 first, and then y squared minus x. I'm going to record two quotients, like before. Well, I'm not going to give them names. The first one corresponding to this one, and the second one corresponding to that one. And I may have a remainder, so let's start. Leading term, we divide by the leading term, we get xy. Multiply back, x squared, y squared, minus xy. Subtract. And then I have to take, let's see, minus y cubed is going to come first, and then plus xy, right? Next, y cubed, we divide by y squared, we have a minus y left. Oh, sorry, I skipped ahead. This is not divisible by xy, right? But it is divisible by y squared. So I divide by y squared, a minus y survives. I multiply back, plus xy. Well, now everything goes away when I take the difference. So my remainder here is 0. So what's the problem? Switching the order of the elements in my tuple gave me different results. In particular, at this stage, we cannot rely on the remainder being 0 to decide if f belongs in the ideal generated by f1 and f2. Because it looks like it does, actually. We can write it out. If it's okay to push this board up, then I guess we're saying that f is equal to xy. Well, the first one there is really the one I called f2 minus y f1. So it belongs in the ideal that those two polynomials generate. Okay. All right. So, oh, I probably should have had this one first. Well, while I was doing the problem, really, these are the steps. So it's an algorithm, it's well defined, and these are the steps. If you want to formalize them or code them, you could go by this. Yeah, so these, it's kind of annoying when you have to write it in general, but what we have done here is you take the leading term, you divide by another leading term, and you get the monomial that survives. So sorry about that. When am I supposed to finish again? 10:20. Thank you. All right. We're doing fine. Okay. So now, having seen this kind of phenomenon, you can divide a polynomial in two or more variables by a tuple of polynomials. Yes.
I just have a question.
Yeah.
This last comment you made about f actually being the ideal, is that just a coincidence, or is this as a
yeah, well, the moment you can write it like this, it's in the ideal, right?
Yeah.
So I chose this example specifically so that this would happen.
The division algorithm didn't tell us anything about that?
At this stage, the way we have done it, we cannot use the remainder being 0 as a criterion to decide if f belongs in the ideal or not. But we're getting there. Right? So what is going wrong actually in here? You might say, okay, the algorithm, maybe the problem is in the algorithm. Okay, it turns out it's not really there. In a sense, the problem is in the set of polynomials that we chose to generate the ideal. Okay. Somehow we see that even just switching up the order of those generators can lead to different results for the remainder. We don't want that to happen. If the remainder should be 0 because the polynomial is in the ideal, it should be that consistently all the time. And not only that, I showed you one algorithm, but maybe one of you one day will come up with a different algorithm, and still we would all want to agree that no matter how you compute this division, the remainder should always be 0 if the polynomial is in the ideal. Okay? Well, here's where these particular generators called Grobner bases come into the picture. So the problem wasn't in the algorithm, the problem is in what you're dividing by. And I'm giving you this definition. If you have seen Grosvenor basis before, this may not be what you might have seen first of the definition. It's equivalent, but I would say it's potentially a little more straightforward in this picture that I'm trying to give, in this narrative of the motivating problems we had at the beginning. We really want to use the remainder being equal to 0 as the criterion to decide if a polynomial is in the ideal or not. And in fact, you can make this definition even without knowing what the ideal is just yet. So I'm going to take my polynomial ring and fix a monomial order. Then I'm going to take a tuple G of non-zero polynomials, and I'm going to call it a Grosvenor basis if for any polynomial f, when I divide f by this tuple, basically I get a unique remainder. Again, when I say it this way, it's not entirely precise, right? Because when I say you divide f by the tuple, I'm implicitly saying you should use the algorithm that I gave you in the previous slide, right? But even if you use a different algorithm, if you do it in any other way, you should still all get the same remainder. So the better way to say this is that given for every f, there is a unique polynomial little r that we can still call the remainder, with the property that f is a linear combination of the g's in the tuple with some polynomial coefficients, again, I can call them q's, plus r, and the r is either 0, or if it's not 0, it must be so that none of its terms are divisible by the leading monomials of the g's. Of course, if you use the algorithm I gave you, this will already happen. And then more specifically, if these polynomials G1 through Gs generate an ideal that you call I, we're going to say this is a Grosvenor basis of I. Okay? All right. Do we have any questions on this definition? Yes.
So the uniqueness of the remainder is enough for this to be equivalent to the
yes, the uniqueness satisfying these properties. Yes, exactly.
I like that because it emphasizes why we care.
Well, I mean, I designed the narrative, right? So I control the narrative, so I can emphasize this. It's quite convenient. But I will say this, the other definition that if you're taking a course on this stuff, right, you really need to prove stuff. And this is not necessarily the best definition if you're going to prove stuff. So to be fair, there's a reason why you're given other definitions. But yes, there are different equivalent characterizations of Grosvenor basis. Okay, so in fact, the rest of my time today, I'd like to tell you a little bit about how you go about recognizing a Grosvenor basis and maybe even finding one. So I'm going to give you this other definition. It looks a little bit scary. There's a lot of stuff floating around, but it's not too bad. You take two polynomials, f and g, and well, okay, you still need to have a monomial order fixed from the beginning. We introduced this notion of an S polynomial of f and g. What this is a polynomial that is designed to create a cancellation of leading terms. So basically, f and g will come with their own leading terms, right? But if you multiply by the appropriate stuff, you can get to a common monomial. And then if you multiply by the right stuff and you take a difference, that common monomial will disappear. So that's exactly what this S polynomial is designed to do in a sort of minimal way, which it achieves by this leading common multiple of the leading monomials of f and g, and then you divide to get whatever you're missing. You need to divide also by the leading term because you want the leading coefficient to cancel out so that both things have coefficient 1, and in the difference they actually disappear. We're going to do an example so that hopefully this makes more sense. Let me also point out that because it's a linear combination of f and g, this S polynomial belongs in the ideal generated by f and g. Okay, so let me do my example here. I might even be able to fit it down here. I think I'm trying to reuse the same stuff. So yes, I'm reusing the same polynomials. So let me say this one here is f1. Remember, we switched the order. So this one is f2, but I'm going to use those. And I'm going to use always the graded lexicographic order. So when you compute the least common multiple of the leading terms of those, well, okay, this one is y squared, this one is xy, and so it should be xy squared. And so what does this S polynomial look like for F1 and F2. So I'm going to have to do, so I have my F1, which was y squared minus x. And well, if I follow my definition, I should put this here and divide by y squared. Minus, I have my F2. And again, here, I want to put this and divide by xy. So again, what survives in this division is just x. And then I multiply it with this and I get xy squared. Here, what survives with this division is y, and I multiply here and I get xy squared. So when I take the difference, this first column will give me nothing. And so really what I care about is the rest. So now here we said an x survives, right? So x times minus x. So minus x squared. And here I have a minus y times 1, so plus y. Okay? So this is the S polynomial of F1 and F2. And hopefully now that definition makes a little more sense. Yes? It might stand for syzygy. Subtraction, thank you. Yes. So I'm not sure that with this S actually everyone agrees. Anyways, so I'm just gonna say S, and you fill in the rest. All right. Okay. So once we have these S polynomials, we can actually come up with a criterion to recognize a Gröbner basis. Not yet construct, but at least recognize. So again, I told you the definition before that I gave you for Gröbner basis isn't necessarily the most practical to check. You would have to divide every polynomial and make sure the remainder is uniquely determined, not quite achievable. But it turns out that a tuple G, G1 through GS of non-zero elements is a Gröbner basis if and only if for all different indices I and J, when you take these S polynomials as constructed and you divide them by the tuple G and the remainder is 0, that's it. Okay, so that is what we're aiming for here. Of course, yes. Yes, I guess that's a good point. I never really thought about that, but I think the issue comes when you switch the order of the tuple, right? If you switch, so this is the order that matters in a sense. Well, it won't, but, and this one doesn't matter so much because even if you switch I and J, you're writing things out, but then you reorder them using the monomial ordering, right? Yes. Oh, yes, the order on G is fixed. Yes. Yes, exactly. Yes, so because it satisfies the definition in particular, even if you did another division where you switch the order of the elements in G, because it's a Gröbner basis, or if it is a Gröbner basis, the remainder should still be 0. Even if it is not a Gröbner basis, under some order it might give a remainder 0, but then under some other order it might not be 0. That's okay, but the criterion says if there is one ordering of these such that all the remainders are 0, then it is a Gröbner basis for sure. The remainder will be 0 even if you permute them. Yes, that's an important point. Thank you. I think my understanding was the order of the G1 through GS. Yeah, of course, the monomial ordering is fixed, should be fixed throughout. All right, so in my ongoing example, I suppose we start with F1 and F2, we get the S polynomial, and now we should, well, let's backtrack for a second. We did the division of a certain polynomial F by F1 and F2, right? We did it in one order and we did it in another order and we got different things. This tells you that F1 and F2 cannot be a Gröbner basis, okay? All right, but then we can construct the S polynomial of f1 and f2, and I might want to give it a name, f3. And now I might not do this. Maybe you can do it later if you want. It might be one of the problems. But if you take together f1, f2, and f3, that is a Grödner basis. So basically, this computation says, okay, you have f1, f2, f3. You compute the first S polynomial of f1 and f2. Now take this one and divide it by the tuple f1, f2, f3. Of course, when you divide by the tuple, you're going to capture it through f3. And so the remainder should be 0. And then you should try the other ones, f2 and f3 and f1 and f3. I'm not going to do this. It's all more of these divisions and S polynomials, but it will give you a Grödner basis. Okay. All right, so this is called Buchberger's criterion, is a practical way to check if you have a Grödner basis. But then I guess the question is, how do you go about finding a Grödner basis if you don't have a good candidate set of polynomials? All right, well, there is another algorithm that you can use. It's not the only one, but this is the format that I could best fit on a slide. It's probably good for theoretical purposes. It's not good for implementation, so warning if you are planning to write any code. But this is sort of the most basic way to get at a Grödner basis. So again, you start with your polynomial ring. You fix your monomial order. Suppose you have an ideal I generated by some polynomials f1 through fs. In my example, that could be f1 and f2. You call that the tuple G. It may not be a Grödner basis, but we're going to build it up to become a Grödner basis. So what you do is, for each pair of polynomials p and q in the tuple that are different, you compute the S polynomial and you divide that S polynomial by G. So like I told you already in the previous step. And then once you have all of these remainders, you look at them. If they're all 0, then we have a Grödner basis by the criterion on the previous slide. Otherwise, you have to take all these non-zero remainders, which you computed, and throw them into the tuple. Right? So your tuple was f1 through fs. So if you go through one round of this, then maybe you're going to have other polynomials, fs plus 1 through ft. And then you do this again. You have more pairs to compute. You compute S polynomials again. You divide. If all the remainders are 0, then you're done. Otherwise, you're going to have more remainders to throw in. And then this could keep going for a while. But eventually, this will stop and it will give you a Grödner basis. Of course, you actually have to prove this works, that it is correct, so that the answer is actually a Grödner basis. You have to prove that it terminates. You have to prove this procedure doesn't go on forever, so that you're not stuck in a loop. But you can prove all this stuff, so this will finish. There are plenty of optimizations you can do. This is not the algorithm that is coded in Macaulay 2 or Singular or Magma or any software that computes this stuff, because this would be terrible. There are lots and lots of optimizations that do not fit on a slide or 2 or 3. I should also say maybe at this point that some of the algorithms are variations or improvements of this one, but there are also other algorithms that are significantly different, and they can give pretty good results. I'm not really an expert in some of that stuff, so I'm not going to try to talk about those, but there are other ways to compute Grödner basis as well. So actually, I wonder maybe if we should do one of those. Well, I have only one slide left, so let me finish here. Maybe we'll finish a couple minutes early. So I will say this, maybe let me take a moment to comment about the problems. So with the problems, the order I wrote them in is following the order that the material appears in the notes. But then you will see at the beginning, you'll have a bunch of problems on monomial orders. So those problems on monomial orders, I tried to order them from easiest or to hardest, or something approximating that kind of criterion. There's some problems that ask you to compute Grödner bases. And if you haven't done this kind of computation before by hand, you should do it at least once in your life by hand. I think it's informative. My examples are not particularly long, so you should be able to finish within a short period of time. And then from the next day on, we will compute Grödner basis with some software. You don't want to do it by hand all the time. there is, I think I mentioned at the beginning, there is one problem about a monomial ordering. I think that's problem 4. And everyone should have a look at that because we're going to use that. It defines a new monomial ordering, and we're going to use that on day 2. Okay. So then let me conclude here with this other slide. So I think we might still be able to see this from, hopefully it's still there. Or I might need a new example. Oh no, we can see it from here. We can see it from here. So we have this polynomial f3. Its leading term, remember I'm doing glex, so its leading term is minus x squared. Okay. Now let's compare that with the leading terms that we had. So this f3 is expressed as a linear combination of f1 and f2, right? It's the S polynomial, so by definition, it is a linear combination of f1 and f2. And maybe for clarity, let me just put the actual quotient here so you can see it a little bit better. This was x, and this here should be just y. Okay, so this has leading term minus x squared, or leading monomial x squared. Can I capture this from the leading term of either one of these? Well, this one will have leading monomial x times y squared, right? So different. And this one also xy squared. Okay, it was designed to produce a cancellation, so it makes sense. But the leading monomials here are different from the leading monomial here. Okay. However, this cannot happen if you generate your polynomial, whatever it is, f3, using a Grobner basis. So this phenomenon is sometimes called special generation. So let's go through here. Suppose, let G be a tuple G1 through GS. And it turns out that G is a Grobner basis if and only if, whenever you write a polynomial as a linear combination of those G's, the leading monomial of the F must be the largest of the leading monomials of these products you see on the right, Qi, Gi. Okay, I guess my Q's here would have been the X and the Y, right? But we see this doesn't happen. F1 and F2 are not a Grobner basis. But if you have a Grobner basis, then the leading monomial is always captured by the leading monomial of one of the things on the right. And this phenomenon of special generation actually leads into the other definition you may have seen before if you work with Grobner basis, which is the one that has to do with leading term ideals. And we'll come to that later in the week. But this is sort of getting there. And this is a complete characterization. So G is a Grobner basis if and only if this happens for every polynomial f. And I think it's okay to stop here.